So today we're going to have a quick lesson on redox reactions. We're not going to go too in-depth with it. We're going to go in-depth with it more at the end of the year, but I still want you to know how to list oxidizing numbers, okay, which we did a little bit at the end of last year. Okay, so we are talking about redox reactions, right? Redox reactions just mean they are reactions that involve reduction or oxidation, or a transfer of electrons. So, what is oxidation reduction? Okay, oxidation reduction reactions, okay, or redox is just a reaction where electrons are transferred. Okay, so it's kind of like a reaction where oxidation numbers changes, which we'll talk about here in a second. And I need a new marker. Okay, so we have to know the difference between redox or reduction and oxidation. Okay, so what is reduction and what is oxidation? Reduction is when an atom gains electrons. Okay? And oxidation is just the opposite. Oxidation is just the opposite, okay? Is when an atom loses the electrons. Okay? And you need to know the difference between these, but sometimes we get confused. Okay, so I have a saying, I should say the chemistry world has a saying, because I didn't come up with this, is Leo says ger. Okay, Leo says ger, which is losing electrons oxidation, gaining electrons reduction. So it's like Leo the lion says ger, losing electrons oxidation, gaining electrons reduction. There's also oil rig, which is oxidation is losing, and rig, reduction is gaining. Okay, rig, you guys like that word? Okay, so oil rig. Some things we need to know. There's some rules for redox reactions. Okay, what we're doing mainly for this is labeling oxidation numbers. Okay, so if we want to label oxidation numbers, we need to know the rules for them. And the first rule is elements in their neutral state have an oxidation number of 0. Okay? So when we see compounds or atoms that are by themselves that don't have a charge, we're just going to assume their oxidation number is 0. So something like Na, no charge listed, we'll just say that's oxidation number is 0. O2, we are giving the oxidation number on the individual atom. So O2, each of those oxygens is just going to have an oxidation number of 0 as well. There's no stated charge. They both must have an oxidation of 0 since they have to be the same in order for that compound to be 0. O3, no charge given. All those oxygens must have a 0. Let's go with P4. Okay, again, it's neutral, no stated charge. All those phosphorus atoms have to have an oxidation number of 0. Rule number 2. Ions have oxidation numbers equal to their charge. Okay, so if you see an ion by itself, its oxidation number is just its charge. So if I have Na plus this time, its oxidation number is +1. Okay, Okay, if I have Ca2 plus, its oxidation number is plus 2. If I have Cl minus, its oxidation number is minus 1. Now don't get these confused with charges, okay? Charges are what it likes to ionize into. Oxidation numbers is when it's in a compound, how many electrons it's surrounded by and what charge it gives it. Okay, it's not always its charge listed on the periodic table. And we'll get into that here in a little bit. But rule 3, okay, rule 3, you know what, I'm going to say it this way, I'm just going to minimize it. Hydrogen is always plus 1. Okay, hydrogen is always plus 1. There's an exception, and that's when it's a hydride, when like it's with NaH. Okay, in this situation, Na has a plus 1 oxidation number, hydrogen has a minus 1 oxidation number. That's the only time you'll see hydrogen having a minus 1 oxidation number. Usually, the rest of the time, it's got a plus 1 charge. And then rule 4, oxygen has an oxidation number of 2 minus, okay, or minus 2. So it's got an oxidation number of 2 minus. Okay, there is an exception to this as well. And that's just when it's in hydrogen peroxide. Okay, in this case, hydrogen has a plus 1 oxidation number, oxygen has a minus 1 oxidation number. Okay, so again, hydrogen always plus 1, oxygen always minus 2, except for those two specific instances. And then 5, as I like to revert if you can't use any of your rules, it's just when all else fails, revert back to charge. Okay? So if there's nothing in there that follows any of our rules, you could just use the charge as the oxidation number. So if you have a situation like NaF, it's like, okay, so that's not an atom that's by itself without a charge. It doesn't have a stated charge. It doesn't have hydrogen or oxygen in there to help me. I'm just going to revert back to the charge. Okay, I'm going to say the oxidation number on sodium is plus 1, and the oxidation on fluorine is minus 1. Okay, so they're by themselves with no charge, oxidation number is 0. If they're by themselves and they have their charge, the oxidation number is their stated charge. Hydrogen is always plus 1, except for this exception. Oxygen is always minus 2, except for hydrogen peroxide. And then when all else fails, revert back to charge. Okay? So most of the time what you're going to see is you're going to see compounds paired with hydrogen and oxygen, and that's how we're going to list oxidation numbers. So let's go ahead and let's do a few examples so you can put this to the test and understand kind of what I am talking about. Today I want the oxidation number of each atom in H2CO3. Okay, so this is the kind of question that I'll be asking you. What's the oxidation number in all the atoms in H2CO3? Or list the oxidation numbers for all the atoms in the compound. Okay, we are splitting this up into H, C, and O. And again, the oxidation number is just on one of the hydrogen atoms. I know there's 2 in that compound, but I only care about the oxidation number on the individual hydrogen atom. So, what do we know about hydrogen? What is hydrogen's oxidation number? It's always plus 1, right? It's not a hydride here, right? It's not the second element, so it's plus 1. Oxygen is always minus 2, right? It's not a peroxide, so it's always minus 2. So then carbon's the tricky one, right? We don't have a rule for carbon, so what we do is we just use the surrounding charges, or oxidation numbers I should say, to help us determine hydrogen, right? Or carbon, sorry. If hydrogen is plus 1, that means total it was plus 2 up here. If oxygen is minus 2, that means its total is minus 6 here. And this whole compound is neutral, right? The whole charge is 0. So what must carbon equal in order to get this whole compound to equal 0? It has to be plus So the oxidation number on carbon is +4. Okay, so that's kind of what we're doing. And again, this is our answer down here, those individual oxidation numbers. H2CO3, list the individual oxidation number on each one. Go to your rules and then use the surrounding oxidation numbers to determine the oxidation number of whatever element is left over. Let's do another one. ZnOH4, and overall it's got a 2- charge, okay? So that whole compound has a 2- charge. We got to match that 2- charge. So in this instance, I have Zn, I have oxygen, and I have H, okay? Again, luckily, we know oxygen is always 2- or -2, and hydrogen is always +1, all right? So now we got to figure this out. We got to combine all these guys and make sure I match that 2- charge at the end. Let's see, hydrogen has a +1, I have 4 hydrogens, so that means I have a +4 charge on all of those. Oxygen is -2, I have 4 oxygens, so that means I have a -8 oxidation number on all those. So again, remember, we are trying to match this 2- charge on the top. This one, it was neutral, so we just had to neutralize it. But in this one, it's got a 2- charge up top, so we got to match that 2- charge. So what must zinc equal? I would say +4 if I want to neutralize it, but I don't want it to be neutral. I want it to be 2-. So I'm just going to say it was +2, right? 2 + 4 is +6 -8 gives me that total charge of 2-. So that's my answer right there. We have NO2-, okay? Here I only have 2 compounds, N and O. I gotta match a -1 charge at the very end. I know oxygen is -2, okay? Again, all these guys are -2 for each oxygen, so altogether it'll be -4. And remember, I gotta match that -1 charge, so that must be that nitrogen is +3. Okay, +3. And then this is the instance where you say, okay, now I realize that this isn't just the charge, right? Because nitrogen's charge is -3 on the periodic table, but in this case, its oxidation number is +3. Okay. Next thing. Now we have to combine all this together. We got to figure out which one is oxidized and which one is reduced, and this happens in a chemical reaction. So let's go ahead and do just 3 examples. Okay, this will be example A, as I get my hands all black from this marker. What you'll see, or what I'll like to ask you, is that I'll give you a reaction. And I'm going to make this real simple for the first one. And I might say which species, which compound, which ion is reduced and which one is oxidized. Well, we are going to use a combination of Leo says Ger and our oxidation numbers, okay? So again, the question is going to be which species, which reactant is oxidized, which one is reduced. Okay, we got to assign oxidation numbers first. So let's go ahead and do that. So I'm looking at all these species and I'm going to give the oxidation number. Well, these guys are all by themselves, so they're just going to be their stated charge. Chromium has a +1 charge, so its oxidation number is +1. Tins is +4. Chromium by itself over here is 3+, and tins over here is 2+. Okay? So again, we're trying to figure out which species is oxidized, which is reduced. So we're looking at the compound or the ions on the left side of the reaction and on the right side of the reaction, seeing what happened between those two. So let's look at chromium. What happened to it? It went from a +1 oxidation number to a 3+ oxidation number. So what happened? Was it oxidized or was it reduced? Well, remember, losing electrons is oxidized and gaining electrons is reduced. Usually what I like to do is I like to find which one was reduced, which one gained electrons, right? If something gains electrons, it becomes more negative, or it loses that positive charge, right? So if something gained electrons, it was reduced. Well, which one of these species, chromium or tin, gained electrons? Which one became more negative? Wasn't chromium, it became more positive. So tin became more negative, right? It went from a +4 oxidation number to a 2- oxidation number. It gained electrons. It was reduced. So you always just put the reactant species. So here it was SN4+. So this guy was reduced because it gained electrons. It became more negative. That means that chromium +1 had to be oxidized. It lost electrons, right? When you lose electrons, you become more positive. So in this case, chromium became oxidized. All right? And again, you just put the original reactant it came from as which species is reduced or oxidized. So here's our next example, right? And again, I'm asking you which one's oxidized and which one's reduced. Well, let's give the oxidation numbers, okay? Hg, it's just a stated charge, right? +1. And again, we don't care about all of them together. We just care about the individual atom. So this one is +1. Iron, it's got no stated charge, so it must be 0 for its oxidation number. Same thing over here with this mercury, it's by itself, so it must be 0. And that iron has a stated charge of +3. So again, we're looking for which one's reduced, which one's oxidized. Again, reduced is easier in my book. Which one became more negative, which one gained electrons. Well, from Hg to Hg, it went from +1 to 0. It became more negative. It gained electrons, right? So I'm going to say that Hg plus was reduced. And then I look at iron, right? It went from 0 to +3. It lost electrons. It became more positive. So that means that Fe is oxidized. And again, you don't put Fe3+, you put Fe. It's the one on the left. All right, and here is our other example, right? And this is a situation where you're going to have species that maybe don't get reduced or oxidized. And you'll see why here in a second. So I'm trying to figure out which species is reduced or oxidized. Let's list some oxidation numbers. Hydrogen is always +1 unless it's a hydride, which it's not. So that means chlorine must be -1, okay? Oxygen is by itself, right? It's usually 2-, but this time it's by itself, right? If we gave oxygen a -2 oxidation number, then that means overall it would have a -4 oxidation number. Well, that's not how it's stated, right? It's by itself, charge isn't stated, so we're going to say it is 0, okay? Don't forget that rule. If something's by itself and there's no stated charge, you're going to say it's 0, okay? Same with this chlorine here, okay? It's by itself, no stated charge, so its oxidation number must be 0. And then on that water, we just revert back to those hydrogen-oxygen rules, which hydrogen is +1, oxygen is -2, which makes sense because it's a neutral compound, okay? So I look at this, right, and I have my H's, my chlorines, and my oxygens. And you could see that hydrogen, okay, it stayed the same. It wasn't oxidized or reduced. It didn't transfer any electrons. So in this case, it's kind of our spectator ion. So in this case, don't worry about hydrogen. So now we're just focused on chlorine and oxygen. Well, chlorine went from -1 to 0, okay? It became more positive. That means it lost electrons, okay? It lost electrons. So if it lost electrons, chlorine was oxidized. Right? So chlorine ended up being oxidized, and then which one became reduced? Oxygen, right? It went from 0 to -2. It gained electrons, so it was reduced. So oxygen is now reduced. Okay? In this case, I've seen it both ways. So you could just put the individual element, okay? But I've also seen on AP test questions where people just include where the compound came from originally. So oxygen was reduced, right? Well, it originally came from O2, so they'll put O2 there. In this case, chlorine originally came from HCl, okay? So they'll put HCl as being oxidized because that's where the chlorine came from originally. For my class, okay, and from what I've seen, it's fine if you just leave it as Cl and O in these situations, okay? I'm not going to count you wrong for it. And I've seen on the AP exam that they don't usually count people wrong for it as well. Okay, so if they specify like, hey, make sure to include the original reactant, then do that. But if they're just saying what species is oxidized and which is reduced, or which ion or atom is oxidized or reduced, you could just leave the individual atoms there, like oxygen and chlorine. Okay, so hopefully that was just a little bit of a refresher from last year, and hopefully you guys understood that. Let me know if you have any questions, and have a great day.